Alright, so this is 2012, problem number 3, fluids, dealing with fluids here. So in this problem, if you notice, we're in a state of equilibrium, right? We have water on one side and oil on the other side. So the key here, the key concept is noticing that the pressure at point B and the pressure at point A have to be equal to each other for this to be in balance. If one was greater, it would be pushing it up or pushing it down, right? So they have to be equal to each other. So our equation for pressure is, well, P initial plus rho G H, right? But the P initial is the same on both sides, so you can kind of ignore that. If you don't want to, you could just say, all right, that equals P initial plus rho GH. P initials cancel, right? So rho GH, this is for oil, and this is for water. G's cancel too, don't they? So basically, the rho of the oil, that's what we're looking for, times the height of the oil, 0.272, should equal the rho of the water, which is 1,000, times height of the water, which is 0.245. So that's how you should approach this problem. You want them to be in balance with each other. I mean, conceptually, because this is higher, what should be true about the density of the oil? Should be less, okay? And in fact, it is 901 kilograms per meter cubed, okay? This is worth 3 points. So basically 1 point for the setup, 1 point for the substitution, 1 point for the answer. Yes?
I kind of worked backwards from B to A.
Did you get the right answer?
Yeah. No.
Yeah, it'd probably be okay. Just make sure in your work that you're clear on kind of what you did. Okay, we're looking for the absolute pressure. So question B, find the absolute pressure at point B. So yeah, so I guess you found the absolute pressure at B, and then you found for oil. Yeah, that's perfectly acceptable to do that. So this would just simply be the equation, right? Rho G H. So this would be 1 ATM, that's 1 times 10 to the 5th, plus 1,000 times 9.8 times 0.245. Okay? So you should have gotten 1.02 times 10 to the 5th pascals. 1.02 times 10 to the 5th, yeah. It's a good question. So this is our absolute pressure. So the absolute pressure takes into account the atmosphere above it. So that's like the true pressure at this point, at point B. So that would be the atmosphere above it, which is 1 ATM, plus the pressure due to the water, which is significantly less. But you add those two. So if it just asks for gauge pressure, you would just find rho GH. That would give you the gauge pressure. Okay, so that was worth 2 points. Yeah.
For the initial pressure, I used 1.012.
That would be fine. Yeah.
Okay, because it gives you
A little bit different answer. Yeah. Just so make sure you're showing your work. So you know if you get a different answer than they did, but if you used 1.013 or something times 10 to the 5th for 1 ATM, then you would get slightly different, but similar. So show your work. All right, so that was worth 2 points. 1 point for the setup, 1 point for the answer. Okay, letter C. Okay, so this part was a little bit confusing. I thought this was challenging, this part. So basically they're saying, so this was A, right, and B initially. Basically what they're saying is what are we doing? We're filling up this water with the same volume, and then we're putting it in here. Now how's this going to change? It's going to be less, right? So it's going to be like this, okay? So if that were to happen, this would not be in equilibrium at this point, right? Because if you notice, the pressure is not due to the volume of liquid, it's due to the height of the liquid. So if there's a lower height here, there's going to be less pressure here, more pressure here. So to compensate, this side is going to drop down. Okay, so B is going to move down a little bit, and A is going to rise up a little bit. This would rise up, this would drop down. Okay, so the answer is, what's the answer? Below A. Okay, so B would drop below A. It would end up being a little bit lower. Okay, and the solution, I kind of described it, described the reason. Let me show you the reason that they gave. So you got 1 point if you said below A. You got 1 point for some statements saying the height of the oil above the mercury is now lower. Okay, for a statement that the pressure is lower at interface A owing to that lower height. So some kind of description, either the way I described it or the way that they just described it. So that was worth 3 points. Okay. Letter D, small piece of wood is now placed in the oil so that it floats. So we're putting a little piece of wood here. Indicate whether the pressure increases, decreases, or remains the same. What should happen? Increase. Okay, increases. There's now additional mass, right? So there's going to be more weight. Therefore, there's another force pushing down. Pressure equals force over area. Therefore, the pressure should increase. So some kind of description there. Actually, that was only worth 1 point. They didn't ask you to describe why, right? So 1 point if you got that. And then they added 1 extra point here. So we've only added up to 9 here. And they do this often for correct units in both answers of parts A and B. Okay, so that's the 10th point. In other words, if you said, what was it, pascals? Pascals for part B and kilograms per meter cubed for part A. Yeah.
So for the 3B, the one sentence, what is it?
That was 1 atmospheric pressure.
Is that for pascals?
Pascals, yeah. Yeah, if you just put 1, that's not right, because 1 ATM equals 1 times 10 to the 5th. And that conversion is on your constant sheet,